Wanted to do another example problem of drawing coupling trees, the very best way I know of for students to learn how to understand multiple coupling patterns like doublets of triplets and triplets of doublets. Nothing that I've ever seen makes it clearer how these interesting patterns show up in spectra, especially as you get into larger and larger molecules, than actually grabbing a piece of line paper, or a line blackboard in this case, and drawing a few. So that's what I wanted to show you. So I have an example molecule here, and the lines go to other atoms. I don't care what they are, they're not hydrogen. So we're looking at a system of 4 hydrogens. The one that we're going to focus on here is hydrogen A. That's the one we're examining, and we're going to pretend for the moment that whatever its chemical shift is, it's far away from the others. And it's going to be under the influence of hydrogen C, one neighbor in this direction, and hydrogen B, a group of 2 protons in the other direction. So we have a combination of a doublet influence here and a triplet influence there. And what we're going to do is we're going to consider 3 different cases. The first, what happens when the doublet influence has the larger coupling constant. Here I'm going to use 8 Hertz because that's a nice convenient number. The second coupling constant is smaller but still fairly considerable, 5 Hertz, giving us a triplet influence. Then we're going to switch it around, and what if these 2 coupling constants are reversed? And finally, what happens when the 2 coupling constants are identical to each other? So we're going to start off with this one. And remember, when we do these types of patterns, we always do them in the order from the largest to smallest coupling constant. So we're going to work on the doublet influence first, then the triplet. Together, that will create the doublet of triplets. Because we name the biggest one first, and then the other influences come next. The next one we will do after this one is going to be the triplet of doublets. The doublet of triplets. And it begins here in the center. I'm going to label that. There is the chemical shift of my hypothetical proton A. I'm not going to specify where it is. It could be 2 ppm. It could be 10 ppm. I don't know. I don't care. The other protons, hydrogens C and B, are not there. They're someplace else. And so what I'm going to do is I'm going to take the chemical shift of hydrogen A. And now I'm going to, in my middle of my lined paper here, mark it. And then I'm going to put in the 8 Hertz doublet influence. I'm going to take my signal for hydrogen A, and I'm going to divide it first into a doublet because of the coupling constant between hydrogens A and C. Now, the doublet is an even numbered multiplet. It is, doublets and quartets, sextets have even numbers. And remember, how you work with them is if you have an 8 Hertz coupling constant, at the center, you go half of that coupling constant in one direction, half that coupling constant in the other. And so what I'm going to do is I'm going to go 1, 2, 3, 4, and mark it over there. I'm going to go 4 lines over in this direction. 1, 2, 3, and 4 lines over in that direction. And mark it that way. And I'm going to be very careful about this. 1, 2, 3, 4, 5, 6, 7, 8. Where each line on my lined blackboard, each line on lined paper represents 1 Hertz. So there is J, proton A back to proton C of 8 Hertz. There is an 8 Hertz doublet, taking our one signal and splitting it into 2. Furthermore, the other critical thing that you want to make sure you do here is mark the ratios of the peaks. And you'll see why, as we do more examples, why this is really important. I'm going to put a 1 and a 1, because remember, technically a doublet, each branch of the doublet is equal in size to the other branches. So we have a 1-to-1 ratio of the two branches here of the doublet. Now, after I have done the doublet influence, the major or the most significant influence, I'm now going to turn my attention to the triplet influence, JAB, 5 Hertz, the influence of the group of protons here at B, the equivalent protons, splitting the signal of proton A into a triplet. Now, how you approach this is the following. You take each branch of your earlier coupling pattern and pretend the other branch isn't there for the moment. So I'm going to take this branch and divide it into a triplet. The triplet will have a 5 Hertz coupling constant. Now, the triplet is an odd-numbered multiplet. The pentet and the septet would be as well. So we have an odd-numbered multiplet. What you end up with is a center peak. In other words, the very first thing I'm going to mark is, I usually come down and mark it here, the center. Because unlike the even-numbered one where we took the signal and divided it, half this direction, an odd-numbered multiplet like the triplet here is going to have a center peak. And then I mark the two outer peaks. For the triplets, I'm going to go 1, 2, 3, 4, 5, and mark that position. And then I'm going to go 5 the other direction. 1, 2, 3, 4, 5, and mark this position. And that are the 3 marks of the triplet. Sometimes folks will get confused. They'll say, but from here to here, that's a distance of 10 Hertz. True, but the coupling constant tells you this. JAB is 5 Hertz, the separation between each part of the triplet. JAB equals 5 Hertz here as well. 10 Hertz total across, but this 5 Hertz apart, these two 5 Hertz apart. Finally, the ratio of the peak heights of the triplet. Remember the triplet, Pascal's triangle and all that. 1 to 2 to 1. And that is vital that we keep that in mind. Now that is this branch of the original doublet. It makes a lovely triplet here, but I am not done because I have this branch of the original doublet that I also have to take and divide into a 5 Hertz triplet. 5 Hertz triplet, odd-numbered multiplet. We mark the center position. And then we go 1, 2, 3, 4, 5, and mark here. Oh my gosh, what do I do about all this? Remember what I said earlier. When we work on each branch, we ignore the other one. I'm working on this branch now, so I'm going to ignore, for the moment, the other branch. In other words, I'm going to pretend that this stuff I drew a moment ago isn't even there. Triplet, center, 1, 2, 3, 4, 5 to the right, 1, 2, 3, 4, 5 to the left. And there is, there I am, there is the other triplet. I'm going to mark its ratios again, 1 to 2 to 1. Oh, over here, 1 to 2 to 1. It is easy to get them tangled if you're not careful. And there, that is the 2 coupling influences. Now we draw what hydrogen A ought to look like now that we've done this. Watch what I do, and especially the peak heights. I'm going to start over here at the risk of sliding out of the picture, but here will be our baseline. We have a peak, and it goes up, and I'll call that height 1. And I continue over here, peak height 2. And I continue over, And the next thing I come to is this, the leftmost branch, or the leftmost part of this branch. But peak height 1. Oh my goodness, peak height 1. Peak height 2. Peak height 1. And there is a glorious doublet of triplets. Now, if in the face-to-face class I've often done this sort of thing, I may have done it in a couple of videos, I don't know. This is kind of fun to do as well. You essentially have a signal. That signal is divided into a doublet, and then you take each of these and divide it into a triplet, and notice they're overlapped like this, where this part of this triplet is overlapped with this part of that triplet. And as I was doing all that erasing, yeah, it was kind of a pain in the backside. I realized I probably should have just come in here and painted the lines on here and then said, screw it, because, after all, what are they going to do, fire me? Well, too late now. So we begin again with proton A here right in the center. But this time around, we're going to do the triplet first. We're making the triplet of doublets. Now, for this particular pattern, we're going to do the 8 Hertz triplet. Triplet, odd numbered multiplet, meaning there is going to be this time a center peak right there. And then to do the triplet, you go 8 Hertz over 1, 2, 3, 4, 5, 6, 7, 8 to this position. Over here, 1, 2, 3, 4, 5, 6, 7, 8. And then 8 Hertz the opposite direction. 1, 2, 3, 4, 5, 6, 7, 8. I'll be here. Okay, there is the 8 Hertz triplet. And the peak ratios, 1 to 2 to 1. The 1 to 2 to 1 classic triplet. So there is the first influence, JAB at 8 Hertz. Now we're going to put on top of that the JAC 5 Hertz doublet. That means I have to split each branch of the triplet now into a doublet. Ignoring the others, I'll come to this one and I will create my 5 Hertz doublet. Doublet, even numbered pattern, no center peak. You go half the number of Hertz to each side. In other words, for the doublet here, 1, 2, and a half, 1, 2, and a half. That gives me the 5 Hertz. That's JAC equals 5 Hertz doublet. Didn't even mark this one, probably should have. This is, of course, the JAB equals 8 Hertz triplet. Okay, so this is this branch of the triplet. The triplet divides into a 1-to-1 peak ratio, 1 here, so 1, 1. Now watch this one. The other branch of the triplet is the center, right here. We're making a doublet, even numbered. 5 Hertz total, so 1, 2, and a half in this direction, 1, 2, and a half in that direction. So there's the second doublet of my pattern here. Critical. The peak height starts off as twice as large as the others because we started at a triplet. Therefore, these two will be even compared to each other, but twice as high when compared to that one. Oh man, that is beautiful. And finally, this branch of the triplet. Split it into a doublet, 1, 2.5 this direction, 1, 2.5 in that direction. We start off with a peak height of 1. It's a doublet, so that each side of the doublet is preserved, has the same height as this did up here. There it is. There is the setup for the triplet of doublets. Notice this is going to be different than the doublet of triplets. It does matter what order you take these in, and that's why the name changed from doublet of triplets to now triplet of doublets. Now let's draw it. To draw it, I'm going to start off here again. Here will be our baseline of our NMR spectrum. And we see a peak here, and I'll give it a height and call that height 1. And now I keep going. The next thing I hit is this one, height 1. Now I keep going, and the next thing I hit is right here, height 2. Height 2. Height 1. Height 1. And there is our doublet of triplet, of doublets. A classic triplet, and then each branch also divided into a doublet. Now, there is a third example problem that I want to run through, and it's going to be exactly the same structural fragment here, but it asks this question. What happens when the two coupling constants are identical to each other? So a little more erasing, which is going to make it even slightly messier up here, but we'll deal with it. And let's take that one. Well, here we are now, and still a little messy, but what can you do? Now I want to do this situation where we have exactly the same setup, but now the two coupling constants, the triplet influence from proton A back to B, and the doublet influence from proton A over to C are the same. And I'm going to use 5 Hertz because it's a nice pretty number to work with as my coupling constant. And to do it, I'm going to take the triplet and then do the doublet. Frankly, and if you did the doublet and then did the triplet, in this case, since the two coupling constants are identical, it will make no difference in the final result. So I'm going to do the triplet first. We'll get the biggest one out of the way first. Again, the chemical shift position of proton A. I'm going to do a 5 Hertz triplet. Triplet, odd numbered pattern, meaning I will have my center peak. And then 5 Hertz, 1, 2, 3, 4, 5 to this position, 1, 2, 3, 4, 5 to that position. So for this example, there is J, A, B equals 5 Hertz. And it's a triplet, 1 to 2 to 1 peak ratios. Okay, very nice. Now we're going to do the doublet influence. And again, that means I have to take each branch of my triplet and divide it into a 5 Hertz doublet. 5 Hertz doublet. Even numbered patterns, half to the right, half to the left. So I'm going to go 1, 2.5 to the right, 1, 2, half to the left. It's a doublet, so the peak heights will be 1 to 1. Next branch of the triplet from the center peak. Doublet, even numbered, half one way, half the other. 1, 2, half. Want you to notice they intersect right there. Interesting. 1, 2, half this direction. There is the total JAC equals 5 Hertz coupling constant for the doublet. Now watch this carefully. This branch comes off of the center peak of the triplet, the one that has 1, 2, 1 double peak height. That means This one will have a peak height of 2. That has a peak height of 2. And yes, they are overlapped. Yes, they are going to add together. Come back to that in a moment. I do have the third branch of the triplet to deal with. I'm making another doublet. 1, 2 and a half to the right. Oh my gosh, another overlap. 1, 2 and a half to the left. Peak height of 1 each. Now, it's this overlap that makes this thing so striking. Here's how you draw the resulting pattern. I come along in the baseline and I say, oh my, a peak here with a height of 1. There it is. I come along until I hit this point right here, and I'm going to draw another peak. What will the peak height be? 2 from this branch, 1 from that branch, 3 total. Wow. Another one. 2 from this branch, 1 from that branch, 3 total. And then another peak, height of 1. Do you see what just fell out? A quartet. A 1, 3, 3, 1 quartet. It's just so beautiful when that happens. Yes, indeed. Should be no surprise. If you're a proton and you have 3 neighboring protons, but here's the kicker, all with the same coupling constant, you're going to form a quartet. Whether the 3 neighboring protons are all on the same carbon, and this would have been a methyl group, or on different carbons like they are in my example here, doesn't matter. If the coupling constants are the same, then we're back in the nice, pretty 1, 2, 1, 1, 3, 3, 1 quartets, 1, 4, 6, 4, 1 pentets, all of that glorious textbook coupling pattern stuff that you may have learned of previously and certainly have been talking about here. Now, I'm not going to do it. It would be a nice exercise. Anyway, if we did it in the opposite direction, what if we did the doublet and then the triplet influence? We will come out with exactly the same pattern. A quartet will emerge. And finally, let's take a look at some real spectra, some proton spectra, some actual molecules obtained here at Southern. The first up that I want to take a look at is the doublet of triplets. And one of my favorite examples of this pattern comes out of the proton NMR spectrum of nicotine, of all things. It's in the aromatic region of nicotine. And it is just a lovely doublet of triplet pattern. Now, in this case, the coupling constants are such that the doublet influence is fairly large and the triplet is considerably smaller. So earlier I was kind of waving my fingers around and doing this sort of thing. In this case, it looks to me like they are, or the triplet influence is quite small, but there is definitely the doublet of triplets here in this spectrum. The triplet of doublets. One of my favorite examples of this particular resonance comes out of the proton NMR spectrum of heptaldehyde, and it's this resonance here where you have the classic setup. In one direction you have 1 neighboring proton, in the other direction you have 2 neighboring protons. They have quite different chemical shifts. Here the triplet influence is the larger of the 2, the doublet influence is smaller. So there is the classic, there's the triplet, but divide each one of these into a doublet. The very lovely triplet of doublets of heptaldehyde. And finally, a quartet showing up in a molecule that is not coming from having like 1 neighboring methyl group. It comes out of 3-methyl, 1 butanol, and it's this resonance here, and it's again the classic one neighboring proton in this direction, two neighboring protons in that direction, but here the two coupling constants are identical or nearly identical to each other, giving us this very lovely textbook quartet pattern in the proton NMR spectrum. So there it is, drawing coupling trees. A fairly careful look at some of the variations, some of the things to think of as you draw them. There is no better tool to start to understand multiple coupling patterns, how these things can combine to form all kinds of interesting things with some real live example molecules. Hope this was helpful. We'll talk to you again later.